Hello everyone, welcome to this webinar on how to automatically detect concurrency issues in automotive software. Thank you everyone for attending this. Let's start. So what can you expect from this webinar today? I will show you a methodology how to fuzz automotive software. Of course, this is a very, very broad spectrum. So let's talk a little bit more. What exactly are we talking about? I will show you how to fuzz targets that expect CAN messages as inputs. I will show you how to fuzz targets that are running in a separate thread. And this can also then similarly also be applied to applications that in general run in multiple threads, so multi-threaded. And those applications often can have concurrency issues because of all the different threads that are doing different things at the same time. Also, while doing this, I will show you some general tips on and best practices on how to fuzz your software. Those three things I will also show with an example. So we will actually see some fuzzing here today, but there will also be some things that will only be shown theoretically. What's not covered today is how to stop the target software and make it run on a different system. So usually in automotive, the software is written to be run on very specific microcontrollers. Those microcontrollers are usually not very powerful. And when you want to fuzz something, you usually need very powerful CPU at least. So the first step usually is to take the software and make it run on a powerful hardware so that you can test many inputs per second. We already have some content for this. We also already had some webinars about this, so this will not be covered today. And also today it will not be covered how to write additional bug detectors to uncover more abstract bugs or concurrency issues. So per default, we will be able, or we find all kinds of memory issues like buffer overflows or similar things. You can also use fuzzing to find way more abstract bugs. For example, a state machine that gets into a weird state, which is also a very common type of concurrency issue. But because this would take just too much time to show all of this, today we will focus on how to make automotive software fuzzable, how to make software that takes CAN messages as an input and runs in a separate thread, how to make this even fuzzable. And then the next step would be to identify ways how to uncover even more abstract bugs. So this might be a second webinar, but this will not be covered today. A little bit about myself. So my name is Daniel Teuchert. I'm an application security engineer here at Code Intelligence. I work in the customer success team, so I help our customers here. Some background, I have worked as a penetration tester and information security consultant, and I have, together with others, worked on the feedback-oriented grammar fuzzer called Nautilus. My responsibilities here at Code Intelligence are to show our customers the value of CI fuzz, onboard them so that they really integrate CI fuzz in their DevOps. And this also usually includes identifying the best approach to fuzz customer code. I've worked a lot with our automotive customers, so I've gained some experience here, saw some of the common issues, and found some of the solutions to overcome them. Let's start with a brief recap on feedback fuzzing. So just that we are on the same page here. There are different ways, different techniques or different fuzzing techniques. We will today only talk about feedback-based fuzzing, or white box fuzzing, or smart fuzzing, because this usually, when you have the source code, is the most efficient and effective way. So the basic idea of fuzzing your system under test is that you have your fuzzing engine, you have your system under test, and the fuzzing engine will generate inputs, feed them to the system under test. The system under test will process these inputs, and then the fuzzer will check if the system under test behaves weirdly. So for example, if we have a buffer overflow. With feedback-based fuzzing, we also have this second arrow here. So we have the coverage information that is fed back to the fuzzing engine for every input that it created. So the fuzzer creates one input, executes the system under test on this input, and is monitoring it for crashes. And after this is done, the system under test will feedback some information about which code was actually executed. So how this works is usually during compilation, there will be some instrumentation injected in the system under test that doesn't really change the behavior. It will just add functionality so that the fuzzer will get for every tested input information about which path was taken, which execution path, which code blocks from the system under test were executed. So if a fuzzer generates an input and then gets some feedback that this input actually executed new code, so code that no input before has executed, it will save this input and try to mutate it further. So basically, it's trying to dig deeper and deeper into the system under test to reach the highest code coverage possible. And the good thing is, this actually turns out to be pretty smart. So, for example, there were examples where someone was fuzzing an image parser, starting with just a file that just contained 0. And then after a while, the fuzzer was actually generating valid JPEG images. So we are kind of using the smart mutations here. Okay, so now today we will focus on some specific challenges, some specific tasks or software that you want to test. So you want to test a target application that is running either in a separate thread or maybe a target application that is running multi-threaded, so it has multiple threads, maybe multiple tasks, maybe multiple threads. With running multiple things at the same time, then it can be difficult to really reproduce what you have found. So if you find a bug in a multi-threaded program, usually reproducing it can be very, very difficult. So also the separation from the fuzzing engine from the software under test can make it harder to create fuzz tests that don't confuse the fuzzer. So what's really important is that this coverage information is sent back to the fuzzer when the input was processed. So when the processing of this input is done. So what can happen with applications that run in separate threads is the fuzzer sends an input to the application starts processing it, but then it will process the input in a separate thread. And the thread that took the input returns. So the fuzzer thinks, okay, the input was already processed, then it takes the coverage information, but the input is still processed in a separate thread. So when the fuzzer sends the next input, the next coverage information it will obtain will also contain some information about the second last input that was still being processed. So you need to really make sure that when the fuzzing engine feeds an input to the application, that it can detect when this input was processed completely and there are no leftover artifacts of processing this input anymore. Then another issue might be when you fuzz in Automotive, you very often deal with CAN bus interfaces. So you have an application that expects your inputs on the CAN bus. This might lead to some problems. How do you send a message on the CAN bus? Or maybe the first problem would be, how can you use your fuzzing input, so the input that you get from your fuzzing engine, how can you create a CAN message out of this? Because the input from the fuzzer is usually just a byte array. So how can you make a CAN message out of this? So what's our approach here? For the first problems, those will be mostly explained theoretical, but I also show a little bit practical approach here. You will try to make the software under test as deterministic as possible. So that means on the same input, it should behave the same way. And this can mean that maybe your input also has some information about when which task should be scheduled. So it's not like you should lose all concurrency, or you should lose all the behavior of handling different tasks at kind of the same time. But this is just so that you make sure that when you have one input that is processed by the application, that it will always behave in the same way. For the last point, especially, we will use the FuzzedDataProvider to create a can frame from our fuzz data. That's actually not very hard. And then we will send these can frames over, in this case, a virtual CAN bus to the application that we will test today. So let's talk about the first step, how to make your software under test as deterministic as possible. The first thing is obvious, try to make as much as possible run in a single thread. But of course, you don't really want to change the behavior of your application. What this means is usually you have to write your own scheduler. In automotive software, very often you run your software on like a real-time OS. These OSs usually already have schedulers, and often even these OSs run on single core microcontrollers. So sometimes actually the software isn't really running multi-threaded or two things happening at the same time, but actually everything is happening after each other. So maybe you can also get the same behavior if you just write your own scheduler. And then sometimes you have in these programs tasks that need to be executed in different threads because they don't really return. So they maybe just wait for an event. Whenever that event happens, it will process the event, and then it will wait for the next event. So these tasks, they don't really return. So you need a separate thread for those. So your scheduler should be able to handle this. Sometimes it makes sense to hook or stop some functions like wait for event or something like this to kind of start and stop these threads so that effectively only one task is running at a time. What also really helps is if you can simulate time with your scheduler. So kind of you want to, after you have written your scheduler, be able to tell the scheduler, okay, now let's run my software under test for 50 simulated milliseconds or something like this. And then the scheduler will schedule all the tasks that usually would run in 50 milliseconds on the real hardware. The good thing is with your own scheduler, these 50 milliseconds can be much quicker. So I didn't mention this before, but actually for fuzzing, execution speed is very important. So the more inputs you can test per second, the faster you can get high code coverage. And this is your goal. You want to get high code coverage. You want to find all the bugs hidden in your software. So high execution speed is always good. And this is also the reason why in the beginning I said, usually you take the software that runs on microcontrollers that are not very fast and make it run on powerful machines. So, and the last thing, I think this is also like kind of a general statement. Of course, when you do the hassle and write your own scheduler for fuzzing, you want to make it abstract so that you can reuse it also on other targets. So let's take a look at how a scheduler could look like. So I talked a little bit about what you need to do. This is here's some examples how this then really could look like when you write your own schedule. I won't show like a full implementation of a scheduler. I think this also doesn't really make sense in a webinar, but I hope this will give you kind of the main idea on what is needed. So the first one would be this run for X milliseconds. So this function would be used, for example, in the fuzz test to execute your system for X simulated milliseconds. So again, I showed this in the slide before. You want to try to simulate time with your scheduler. So this function then will try to simulate scheduling all the tasks that would usually be scheduled in, for example, 200 milliseconds. And what it then will do is it will run in this for loop. Maybe this could even be improved, that every task will increase the time differently. In this case, this is very simple. It will just do for every 1 millisecond, it will do one iteration. But this really depends then on your software. So maybe you have different clock or different tasks that take longer or are very quick. So you maybe want to adjust this, or maybe you want to increase the time differently for different tasks. So what you would do then for this time that you specified, you want to take the next task from a queue that you need to manage, and then you will execute the task. And then the next task will be executed, and so on. For this, you then, of course, need the execute task function. How could this look like? If the task that should be executed is a returning task, so it actually returns and doesn't have a while one loop in it, then you can just call the task, it will return, and then you are back to your loop here. If, however, you have a task that doesn't return, then you usually, as also mentioned before, have to start it in a separate thread. And since we don't want to run all the threads all the time, we will actually pause them. And this would be the place where you then will continue the thread. So usually all these tasks, they will be paused. And only when we say, now we want to execute this task, then we will continue to run the task until it will again come to a point where it stops or suspends. Hope this will become more clear with the next two examples. So for example, this would be a non-returning task, and they usually look something like this. They have a while one loop, which they maybe just break out of if there's a shutdown or something like this. And in there, they will usually wait for events to happen, and only then they do something. Usually there are no tasks that do something all the time. Usually they are just waiting for something, then they process it, and then they wait for the next thing. So, and this wait for event function is exactly what you then should hook or stop, so that this wait for event will actually suspend the thread. So you can wait for an event, and when this event happens, you can have a mechanism so that your scheduler will execute the task here, so that it will continue. But then when you come the next time to this wait for event function, then usually you want to suspend your thread. Maybe you don't want to suspend the thread if the event has happened again. This is also maybe up to you to decide. This is just an example. But so this wait for event would suspend a task until it is continued by your scheduler when it's this task's turn again to execute. So this way, you can have a scheduler that will make sure that only one task is running at a time. So you have your deterministic execution, but you still are able to execute tasks that are not returning. So how would this setup then with your own scheduler look like in this fuzz test? So step one would be your fuzzing engine supplies fuzzing data to the software under test. And then you let the scheduler run your software under test for some simulated time so that it can process the input that it got from your fuzzing engine. Step three, I didn't really touch earlier, but this is also important to not confuse the fuzzer. Whenever you are done with processing an input, you want to reset the state for the application for the next input to come. Otherwise, again, there will be some instability. So the next input could trigger some new behavior, but it only triggers this because the input before already set something up. So this is also maybe a side note, you want to reset your application. And finally, you want to start over. So here we have, again, the same image. So in this case, the fuzzer would put its input in here. Maybe you could then have a second error that says scheduler run for 200 milliseconds, and then give me the coverage information and reset the system, and then we start over again. Excuse me. So let's go to the next topic that we had in our solutions. That was regarding how can we supply CAN messages, CAN frames to our software under test. As I said earlier, the fuzzing engine usually will supply its inputs only in the form of a byte array, but we want to create CAN frames out of this. How can we do this? The FuzzedDataProvider is a very neat tool to use this, because you can use it to form your fuzzing data into different data types. And what's also good about this, you can use your fuzzing data at different positions in your code. So you can maybe first take half of your fuzzing input, and then later you use the other half. You just take some individual parts of it. So this is a really nice tool to form your fuzzing data in the form you need it. And some important functions. You need to initialize the FuzzedDataProvider by giving it access to the fuzz data. So this data would be the byte array that we get from our fuzzer, and the size is then the size of this array. And then you can take, for example, individual integrals from your fuzzing data. So with this consume integral function, you can, for example, create a char that is taken from the fuzz data. And if you still have some fuzzing data left, you can consume more of it. For example, you can consume another integer, but this time you can also say, okay, I want to consume an integer in range from 0 to 5. And so this integer here will be 0, 1, 2, 3, 4, or 5. And then you can also do things like consume data, which is very similar to memcopy, where it will just take fuzzing data, or the rest of your fuzzing data, and write it to the address that you specify as the first parameter here. And the second parameter is how much you want to write a maximum. Okay, so let's take a look at an example fuzz test, and then I will also show you the target that we will fuzz today. So this is my fuzz test. For now, let's ignore everything except for this part here, and maybe the function here. So here we have the fuzz test function that will be called by our fuzzing engine. And here we will get the fuzzing data. So our fuzzing engine will generate an input, and this will be the pointer to the data that it created. And this is the size, how much data it created. So we get this byte array here, and we want to use it as a CAN frame. We will fuzz something from the CAN utils project. We will fuzz the CAN dump program, which basically just dumps all CAN messages that it sees on a CAN bus. And to send on this CAN bus, we have to create a CANFD frame. Let's take a quick look at the CANFD frame here. So the CANFD frame is a struct, and it has some members here. First of all, it has the CAN ID. So actually, this also does not only include the CAN ID, but also some other flags. Then down here, we have the payload. And here we'll specify how much of the payload we are using. It also has some flags and some reserved fields. So if we go back, here we want to fill this frame that we initialize with 0. We want to fill it with fuzzing data. So what do? We initialize our fuzzing data, giving it access to data and size. And then, first of all, we want to write the CAN ID. So if we remember, CAN ID, actually we can also see it here. The CAN ID is a 32-bit of size, so it can be a lot of numbers, so that we already have a huge space of input, what it can be. Usually, you want to check which CAN IDs are actually interesting in your project, and then you can only use those IDs. Otherwise, the fuzzer will try all different IDs, and yeah, with this range for 32-bit, this can be a lot of misused CPU power. So I mean, you can be much quicker if you just tell these IDs are interesting. In this case, I've already created an array of the interesting CAN IDs. So those will be the interesting CAN IDs for today. And what I'm doing here is I will write one of those interesting CAN IDs into this CAN ID field, and I will pick it randomly from this array by consuming an integral in range 0 until size of number of interesting CAN IDs minus 1. So basically, I will pick one of those 3 CAN IDs, or the fuzzer actually will pick one of those with some part of its fuzzing input. But we will also use the fuzzing input later to consume a char to fill the flags. And also then down here, we also use the consume data function, where we will write the rest of our fuzzing data into the frame data, so basically the payload. And this function actually returns how many bytes we have written. So we will write this number into the length. Let's take a quick look at the actual target, what we want to test, and then we can talk a little bit more about the multi-threading. So as I said, I've used the CANutils project here that consists of some very useful tools when you work with CAN. I have also added a little bit more code. So I have basically injected a vulnerability that our fuzzer can later find. But for now, let's make a build directory and go into it. And then here we have the CMake lists file where we can build can dump and can send, and where we can also later build our fuzz test. Let's first build the normal can dump. So it builds normally, and we can execute it and make it listen on the vcan 0 interface. I have a second terminal here, which I can then use to, with can send a can message on the same vcan 0 interface. Let's run with can ID 123 and the payload dead beef. As you can see here, can frame is received by can dump, and this is exactly what we want to fuzz. So we basically, with our fuzzer later, we want to send all kinds of can messages to can dump, and then we want to uncover some vulnerabilities. I will stop this here. And before we start, I wanted to show a little bit more how we then send the can frames over the virtual CAN bus. So our approach here would be with our fuzz test, we start the target application in a separate thread. Maybe as you also have seen, the can dump application didn't stop after receiving an input. So this is why we will start it in a separate thread, because it's another target that doesn't return. And the second part would be we will send fuzzing data as can frames to our system under test. And then there's one very important thing. We need to wait for processing of the can frame to finish. So we need to make sure that we know or are informed when processing the can frame is done. fourth point would be reset the state of the application, which is actually not needed in this case because the can dump doesn't really save a state. So that's good. And the fifth step would be to start over at the second step. So we don't have to restart the application. We will just start it once, and then we will just send fuzzing data to it. So to compare it to our other approach with our own scheduler, it's very similar. The only difference here is we have one more step to start the application in a separate thread. And then this point here, I already said, this is very important that we need to make sure that we wait until the can frame is fully processed before we send the next input. Okay, so let's take another look at our fuzz test here. I will actually start it, and then it can run in the background, or it can run here. I can explain how it works, and then hopefully it will find the bug that's hidden here. So this fuzz test was created with CI Fuzz, which is our command line interface that we have open sourced. So you can also use it. You can just go to our GitHub page and download it and install it. This is why here in my CMake lists, I have these add fuzz tests directives where I've added 2 fuzz tests. We will take a look at this fuzz test today. So to run it, I will execute CI fuzz, run, and then the name of the fuzz test, which is fuzz can dump. What happens now is CI fuzz will compile our fuzz test, and it will also compile the software under test with instrumentation. So that's the part that enables us to do the white box fuzzing, do the feedback-oriented fuzzing. And it will also inject sanitizers like the address sanitizer. So if there's a buffer overflow and the application doesn't necessarily have to crash, but the address sanitizer can recognize this and inform us about these types of memory issues, even if the application doesn't crash. As you can see, it's now also running. It's finding more and more paths. So this increases whenever the fuzzer has generated an input that found a new path in the execution flow. Here we have also a timer, how much time it takes to find a new path. When this number gets very high, then you should think about your fuzz test. Maybe you have to improve your fuzz test, or maybe you are actually at the end and there's not much more to uncover. And then here we see how many executions per second we have. 11,000 is quite nice, but it's also not a big application here. And then here we see how long we are running. So how did I create the fuzz test? We have already seen we have this fuzz test function here that will be called by our fuzzing engine. So 11,000 times per second. This function is called and it gets some data. First, I have a little sanity check here. I want at least 12 bytes from my fuzzing engine. Otherwise, I don't even bother to test this because I don't want to send too small can messages. Next step here is very specific for this. So we are setting up a socket to connect to the virtual CAN bus to send our fuzzing data there later. So this is basically just done as it's documented by the CAN utils, creating the socket, binding to it. And then this part we have already discussed. We will create our own CAN frame by using our fuzz data in the different fields. And then finally, here with the write function, we will send our frame. But there's one more important thing here. This processing input variable is something that I have added, not only in my fuzz test, but actually this variable is also, we will find it in the can dump now, because this should show me when the input was processed. So here in this line, we will send the frame, and before that, we send processing input to 1. And afterwards, we will wait until processing input is set to 0. This will be done by can dump. whenever the input was fully processed, and only then we can finish in this function. If I don't have this, then my fuzzer would just send the frame, close the socket, and directly send the next frame. And then we might have these issues with different coverage information from different inputs. So let's take a look where I've put this function in the can-dump file. Let me open this here. And we have just found our bug. Let's take a look at this in a second. So here, this is where I report back to my fuzzing engine that processing is done. So this is 0. And this might require some time to identify a good spot to place this. So in this case, we see, or maybe if we follow this closing bracket here to the top, then we see this is where the events are handled. So again, if I go a little bit higher, here we have the equal_wait function. This is basically where can-dump will wait for incoming can frames. And whenever there are can frames, then it will call this for loop to handle all these events. And finally, once we are here, there's no more processing, everything is done. So this is where I can set processing input to 0. So this is to make sure that every input is executed fully before we take the coverage information. One last thing before we take a look at the bug, the buffer overflow we have just found. We have one more thing here in our fuzz test. We have the fuzz test setup. This would be the step 1 from the slides. Start the software under test in a separate thread. So what I'm doing here is I will execute the fuzz main function in a separate thread because it's blocking. So I will start this function. And then here I have another check. So I wait until the can-dump actually is ready for fuzzing. So this is another variable that I've introduced in can-dump, which we can also take a look at in a second. That will also just report back once the initial setup of can-dump is done. So our fuzzing would first execute, our fuzzing engine would first execute fuzz test setup, start can-dump in a separate thread, and then we will send our frames there. Let's take one last look where I've put ready for fuzzing here. So this is where those variables are declared as volatile. And here I say, now I'm ready for fuzzing. And this is exactly before this equal_wait function. So exactly before we are ready, starting to process incoming can frames, this is where I say, okay, now we can go ahead and start fuzzing. Okay, let's take a look at the crash that we have found. So CI first reports back. We have a finding with name Spunky Porcupine, and we already get some information at the stack buffer overflow in a function called bug1 in can processor this line. But we can also get a little bit more information about it by executing CI fuzz finding and then the finding name. And this is where we get the actual ASIN output. So this is the address sanitizer output here. So we get a lot of more information about this bug. So we see it's a write of size 9. We get a stack trace and a lot of information that can help us to fix this. If I take a quick look at the location. So this is where I've added my toy example bug. So we have a string copy that just copies too much into this buffer of size 1. But before that, to reach this location here, the fuzzer actually has to generate some data that needs to pass all these checks. And so this is just to show really the strength of smart fuzzing. So we didn't tell the fuzzer that it put the string somewhere, but it found this out by itself. So we also have this crashing input. Maybe just to, if I can see this here. We also see that we have stored the crashing input here in this fuzz can dump inputs folder. And if we take a look at it, okay, we cannot, let's try to open it anyway. Okay, it doesn't work with Visual Studio Code, but then let's take a quick look with an hex editor. So if we take a look at just file, fuzz, can dump, and then this one, we can actually see that this file contains code intelligence in here. So our fuzzer really dug deeper and deeper, found every combination until it reached this point and triggered the bug. Okay, I think that was everything I wanted to show about the software that we are fuzzing today, and also about how to fuzz multi-threaded applications. So as a recap, I didn't really show a running scheduler today, but I hope I gave you quite some insights on how you can create your own scheduler to fuzz applications that are multi-threaded and have a lot of tasks that run at the same time. Try to make your application as deterministic as possible so that you can replay your findings and so that the fuzzer isn't confused with the feedback that it gets. The FuzzedDataProvider is a very useful tool to provide your fuzzing data in different formats. That was just one example. You can really use it in many different ways. Very important when you have to deal with multi-threaded applications, make sure that you only test your next input after the last one was completely processed. Otherwise, your fuzzer will get very confusing feedback and it doesn't really know which inputs to keep, or it actually knows, but it knows it wrong. So it keeps the wrong inputs for the wrong reasons, and then it will not be able to dig deep into your application and achieve a high code coverage. So that was it with my webinar. I want to do a little bit of advertisement for our upcoming FuzzCon, which will be held on November 17th. We will have lots of talks about new industry standards in automotive industry, dealing with the increasing dependencies. We have speakers from Carriot, Continental, Argus Security, and ZF. And hope some of you will be joining us there. I also have some more, some links here. So if you want to try CI-Fuzz, the tool that I used today to fuzz this application, as I said, it's open sourced. You can just go to our GitHub and try it. We also have a Java fuzzing engine or a Java fuzzer, open source, which you also can try. And you can also learn more about fuzzing in our blog. Are there any questions? Then I think you can write them in the chat, and I should be able to see them here. Okay, if there are no questions, I hope you found this webinar informative. You could get something out of you for your fuzzing approaches. And I would like to see you again in our next webinar or at FuzzCon. Thank you very much.